The first law of thermodynamics is basically the work energy formula for heat. The formula is given by delta U is equal to Q minus W. Delta U stands for the change in internal energy. That is, confusingly enough, the change in heat energy that we talked about in the previous lecture. Not to be confused with Q, which stands for heat flow. So heat flow represents how much energy in the form of heat transfers into the object. And W represents the work done by the object, specifically the work done either by expanding, in which case work is positive, or contracting, in which case work is negative. And I would like to point out that there is this minus sign here in addition to the sign possibly of work, which means that when plugging this into a calculator, if the object is expanding, then work is a positive value, meaning that you do a subtraction at this step. And if the object is shrinking, that means work is a negative value, which means you end up doing an addition at this step. The second law of thermodynamics. Now, this law has a number of different forms, so I'm going to try to explain them. The simplest form, called the Clausius form, heat does not naturally flow from cold to hot. That is, if you have a cold object and a hot object and they are in contact with each other, heat will flow from hot to cold, but not from cold to hot. Another form, called the Carnot form, says that a machine cannot, as its sole function, remove heat from a system. And the third form, the form that you're probably more familiar with if you pay attention to popular science, is that entropy always increases. Now, each of those statements does have an asterisk, and the first two are pretty self-explanatory, but the third one always struck me as a little circular. The second law of thermodynamics is that entropy always increases. Well, what is entropy? Now again, if you pay attention to popular science, you probably have this idea that entropy is the amount of chaos or disorder something has. An example often given is a messy room has a lot of entropy. I am not very happy with this definition because on the one hand, yes, a messy room is, disorganized. And yes, there is a definition of disorganized that does describe entropy. The messiness of your room is not actually the kind of disorder we use when defining entropy. Specifically, the kind of disorder we use for entropy is number of microstates per macrostate. Now, that still doesn't explain very much. A macrostate is a way that things can be arranged such that they have given macroscopic properties, such as a temperature or a pressure and a mass and a density, and all of those. A microstate represents the number of different ways that the individual particles can arrange themselves. And so any state that has more microstates, as in there are more ways to create that macrostate, the more likely it is. Now, at this point, I am probably being thoroughly confusing. So let's jump to another definition of entropy, and one that actually works a lot better for us in thermodynamics, is that entropy is just a property of material. Everything has a mass, everything has a temperature, everything has an energy, and everything has an entropy. When stated like that, entropy is just a property of the system. We can describe the entropy of the system. We use the symbol S. And we say that that object can have its entropy changing by adding or removing heat from it. And so the formula for how entropy changes with heat is delta S, that is the change in entropy, is equal to the heat added to that object divided by the temperature of the object. Now, it can get a little difficult, especially since adding heat to an object will change its temperature. But if you're familiar with calculus, this is the kind of problem that calculus does fairly easily. Now, using this definition of entropy, we can show how entropy always increases leads to these other two definitions, and in fact, all three of these definitions are equivalent. So let's start with entropy always increases. So, meaning entropy cannot decrease. Well, if the only thing we do is we remove heat from a system, then Q is negative, so delta S is negative. That can't be done. Now, that's not to say we can't remove heat from a system. We can, as long as we add heat to another system. It doesn't even necessarily have to be the same amount of heat. If we're adding heat to a hot system, we would need to add more heat. And if we're adding heat to a cold system, we would need to add less heat. But we still need to add heat to another system. All right, for this first definition, heat doesn't flow from cold to hot on its own. Well, let's consider the scenario where we have a cold object and a hot object. And let's say that heat is flowing out of that hot object and into the cold object. So if it's the same amount of heat in both cases, the hot object loses a certain amount of heat, the cold object gains that certain amount of heat. We can see that negative Q over the hot temperature, and so a hot temperature is going to be larger than the cold temperature, which means that this term is going to be smaller than this term, which means overall the change in entropy is positive. So yes, heat can flow out of a hot system and into a cold system. But the reverse is not true. If we make Q negative here and positive here, then we would get a value that is less than 0, which would mean entropy is decreasing. So heat flowing from cold to hot involves a negative change in entropy. And the third law of thermodynamics is that no system can reach absolute zero. And to explain this, we can look again at the second law of thermodynamics. Delta S is equal to Q over T. This T, by the way, is measured in absolute temperature. So at absolute zero, T would be 0. And what's anything divided by 0? Well, you're not allowed to do that. And you can't get to absolute 0 without approaching absolute 0. And even if you're approaching absolute 0, T becomes really, really small, which means that even removing a teensy tiny bit of heat will cause a massive drop in entropy, which you would need to add way too much heat energy to another system to counter that, and it just doesn't work.